So let's look at section 5.7, electromagnetic energy conversion. So one important use of electrical energy is it can be converted between mechanical energy and electric energy, which is critical to our everyday lives in the modern society. And we will look into the parallel plate capacitor structure to see what happens if you can move the top plates of the parallel plate construct up and down, and see what happens to the energy stored within the structure, or if so what happen? We'll see what happens for various setup of this structure. And the energy conversion that we shall look into is electrical energy converted into mechanical energy, or vice versa. That is, mechanical energy converted to electrical energy. So let's look at what happens in this construct. Here we have a parallel plate configuration, and to the left is a battery, which applies a voltage difference across the two plates. And in the middle, the space between the two plates is not conducting, so you don't have moving free charges between the two plates. So as a result, you will build up positive charge on the top plates and negative charge on the bottom plate. And what is the consequence of this configuration? Because of the presence of positive and negative charge on the two plates, there will produce an electrical force. F equals to QE, right? F 等于 QE 嘛, The electrical force is produced between the two plates. So what happens if you, and note that the bottom plate is fixed, while the top plates can be moved up and down. So if you apply a voltage source, you have positive Q on the top and minus Q on the bottom, and you produce electrical force, Fe, which, without the presence of external forces, will move the top plates down to the bottom. So it will convert electrical energy into mechanical energy, because without any constraints, it will the electrical force will move the top plate and convert it into mechanical energy. In this case, we still have two parallel plates, and again, the top is movable while the bottom one is fixed. If you apply an external mechanical force at the top plate, what you do is you supply mechanical energy and convert it into electrical energy. Why? Because not that there is no battery on the left-hand side. Okay? No battery. So the charges have no place to go. The top plate is populated with positive charge, and the bottom plate is populated with negative charge. No matter the top plate is raised or brought down, the total amount of charges remain the same on the two plates, which means you build up a constant electrical field between the two plates. E is constant. Okay? What happens if the plate is moved up, if the top plate is, if the movable plate is raised, will it increase the amount of electrical field intensity? No. No, because you have same amount of positive and negative charge. However, the voltage, the electrical potential between the two plates is increased. Why? Because V is the product of electrical field times L, or D, okay? The distance between the two plates. So if you move out the plates, what happens? You convert mechanical energy, because the mechanical energy is used to compensate, or is used to do against the electrical force that you found between positive and negatively charged plates. So if you move the plates up, you will increase the amount of electrical energy stored in this structure. Okay? So if you do so, you are converting mechanical energy into electrical energy, which shows in terms of increased voltage, electrical potential. And here is schematic illustrating associated terms, illustrating the terms pertinent to the discussion of energy conversion. To the left-hand side are the source, are the input. They include the mechanical energy input and electrical energy input. The mechanical energy input, as we can see here, is done with your hands. You raise the plates up. The mechanical energy input, the electrical energy input comes from the battery. If there is a battery attached, it may supply electrical energy or it can also store. Well, it can actually supply or store electrical energy in the battery. And on the right-hand side are the so-called increased stored mechanical energy. We don't discuss it, or we do not consider this in this case, because what does that mean if you have mechanical energy? Which means the plate is moving at a constant speed, or a speed that goes up or down. Okay, now because we are doing this experiment very carefully, okay, so the plate is moved at a very slow speed, so you didn't accumulate any mechanical energy in terms of moving stuff. All right, so we neglect the first term. The third is energy dissipated, 摩擦生热之类的事情，so we don't account this term because it's maybe relatively small. All right. So the only term we consider here is the increase or decrease in stored electrical energy in the two plates. Okay, instead of aside from the battery, the two-plate configuration can also store electrical energy, providing that there are electrical charge populated on the two sides of the plate. So the top graph essentially converted to this equation. So that is Fex times dx, the external force times the plate displacement the moving distance of the plate is dx. So the energy equals to Fs, force times distance. And the second term is electrical energy stored in the battery. That will be VI. VI is power rating. Power rating times time, dt becomes energy. VI times dt is in the form of energy. And the very last term is dWe. That is the energy stored in terms of electrical field. And of course, you can have a dWm. But in this case, the two parallel plate configuration mainly only store energy in terms of electrical field. So we consider only the difference in electrical energy. So what happens if we don't attach this structure with a battery? There will be, So here we can simplify this expression a little bit by substituting I dt with dq, which means the change of charges on the two plates. So V dq is the expression for stored energy in the battery. So if there is no battery, the amount of charge do not change. So if you move the plates a little bit, there is no change in the stored energy in the battery. On the other hand, the force is proportional to the change of stored energy in the structure. And you will actually increase the amount of energy stored in this structure. So here we will, I must apologize for the equations. They look a little bit messy in these few slides. So you may spend a little bit more time to understand what it says in these slides. I will recommend you to look directly into the textbook, which give you a more complete story about this part. So this case, in this slide, we discussed the case with battery connected. Because the battery is connected, so the voltage difference between the two plates remain as a constant. The voltage potential, the electrical potential V is held a constant, which means the stored energy in the structure can be expressed as half of CV to the square. C is the capacitance formed by this parallel plate configuration. And V is the voltage between the two plates. So the energy, the stored electrical energy in this structure is 1/2 of CV to the square. And C can be expressed as epsilon A divided by X. So if you substitute V with E times X, then you can find out the stored electrical energy, WE, is this thing. And if you perform a derivative, if you take the derivative of it with respect to x, you end up with this thing. And because so what is the consequence? Because v is a constant, a is a constant, the larger the distance, the smaller the electrical field, and so is the stored energy, stored electrical energy in this structure becomes smaller as well. So you can substitute it so here is the scenario. You move this plate up, which means you supply mechanical energy, but the stored energy within structure becomes smaller. So where does the energy goes? The energy goes to the battery. Okay? You have positive mechanical energy input. You have reduced stored electrical energy. So the result is the stored energy, the energy stored in the battery becomes larger in this case. And with these equations, you can find out the amount of mechanical force, external mechanical force, and the amount of charges and stored in the structure. So in this case, Q can be different. The amount of Q may change if you move the plate even higher. 所以，好吧，整体来讲就是说当你有接电池的时候，你把这个结构的上板往上提。它的结果是外部的机械力有做功所以但是结构所储存的直接在这个电容结构所储存的能量反而变少，为什么？因为上下板的电荷量变少了，那这些电荷跑到哪去？跑到电池里头去所以电池所储存的能量反而增加，它增加的来源有电容结构所减少的能量，以及外部机械施力所提供的能量。好，那 what happened if there is no battery connected to the structure? Again, we apply mechanical force to move the top plate upward. So the mechanical force do input energy. The structure, and there is no change in the stored battery energy because it's not connected. So as a consequence, the energy provided by mechanical force can only be used to increase the stored energy in the structure. So is that true? Let's check. Because there is no volt battery connected, so the amount of total charge stored in the top and bottom plate are not changed, no matter the distance is vary, no matter how far did you raise up the plate. And because the amount of total charges remains as a constant, the electrical field intensity does not change. On the other hand, the voltage difference between the two plates becomes larger and larger as X increases, as the plate distance increases. So the amount of energy increase can be found using this relationship as half times Q to the square divided by A and epsilon sub 0. Okay? So if you balance the equation, in this equation, this term goes away. So if you balance the equation, you can find the required force, the force necessary to move up the plate, It's actually a constant number once you fix the number of charges in this structure. Okay? So with this scenario discussed, let's look at example 5.12. That is an energy conversion example using a parallel plate capacitor. What they do for this in this example is a little bit strange, I must say. But it shows up how energy are converted at a different stage. Okay, so let's check up with this graph. It's moving clockwise from A to B, B to C, C to A. In the first section, that is moving from A to B, the distance between the two plates remains as a constant d. However, the total charge is increased from Q sub 0 to 2 times Q sub 0. So what happens in the course of A to B? In this phase, the battery is charging the capacitor so that the charge density is increased from Q sub 0 to 2 times Q sub 0. Okay? So what happens in the course of B to C? Note that from B to C, the plate is moved up, so the distance increased from D to 2 times of D. If the battery is connected at that moment, the Q, the amount of charge on the top and bottom plate should become smaller. However, look at the graph, the number of Q remains as a constant of 2 times Q sub 0. This suggests the battery is disconnected in the course of B to C. Okay, so in the second phase, the battery is removed. In the third phase, it goes from C to A. As you can see here, the distance is reduced from 2 times D to just D. And the amount of charge is reduced from 2 times Q sub 0 to just Q sub 0. So in the third phase, from C to A, the battery is attached, and the plate is released, so its position is moving from a higher position into a lower position. Okay, so in the first phase, A to B, we are sure that the battery is provide input electrical power into the structure. In the second phase, from B to C, which moves the plates upward, it also stores energy into the structure because you have an external force supplying energy. What happened in the third phase from C to A? The stored energy in the structure is supplied is injected into the battery. Is injected into the battery. Because in the third phase there is no external force. And the stored energy within the structure becomes smaller. So we can ensure that there is some energy going back to the battery. And at the end of this three-phase process, the total charge on the structure is not changed, the position is not changed. So what happened with 所以到底谁出了力啊？这样子绕一圈之后，谁出力啊？你的手啊。好，你手出的那个做的功跑到哪里去了？结构里头吗？电池，对啊。好，电池在那边默默的不讲话，但是它吃了你做的功。好，因为这个 A、B、C 的 process 从头到尾，你那个。你回到 A 那个位置的时候，你的板子的储藏能量没有变，板子的位置没有变，但是那个过程当中，谁出了苦力啊？你的手啊，那个出的苦力，那个 energy 跑到谁身上？跑到那个电池身上去啊，所以你可以用这个方式充电的，有啦，事实上有人有做那种用手握式的那个 USB 充电器之类的，OK， 好 ，All right， so here is what do we do, in terms of equations, to look at this process, So in the first place, you supply, you charge the capacitor, with using the energy in the battery, However, in the second phase, you open up the loop, you disconnect the battery, and you exert external force to move the plate upward. So during that phase, there are mechanical energy input, and it goes into the structure, that increase the amount of energy, electrical energy stored in the structure. And in the third phase, you close up the loop, so and the plate is moving downward, so the amount of energy stored in the capacitor is released into what? Into the battery, because the and so if you calculate the amount of external force, and if you decompose this process into A to B, B to C, and C to A, the amount of energy can be found for each step, okay? In the first step, there is no difference in dx, so it goes away. The second step, you need to exert external forces. External forces like this. So this is the amount of external forces times the distance, which equals to d to 2d. It moves the plates up. So that will be the increased energy stored in this structure. And the second term is the electrical energy output. Electrical energy output to the battery. So overall, you will produce electrical energy output to the battery as this number. 5.6 times Q to the square times D divided by A and epsilon sub 0. Okay. So in the whole process, the capacitor, the two parallel plate construct have no difference in store energy. But the battery, which supply energy during this phase and accept energy in this phase, it's actually accept more energy than the energy it's supplied in the first phase, okay? Now, so, and the supply energy is provided by what? By whom? By the mechanical force, all right? So that's example 5.12, and you recommended look a little bit at it. The very last slide we have here is about electromagnet. And it tells you the external force is also proportional to the amount of energy stored in the gap. Okay, we know in the example 5.11, if there is a gap in your magnetic field system, you will experience a very large electromagnetic field intensity H. The H gap is particularly large. So the large magnetic field intensity can be used to calculate the magnetic energy stored in this gap region. So it's actually 1/2 of mu times H gap to the square times the volume of the gap. That is the area of the gap times the distance of the gap, AX. And you have two gaps so that you can form a complete loop. So according to the amount of magnetic flux and the size of the gap, you can calculate the total energy, magnetic energy stored in this gap in terms of magnetic field. To the force, because of the presence of magnetic energy, and we can find the associated amount of force due to the presence of this stored magnetic energy. So here in this red box, we can calculate the corresponding force due to the presence of magnetic flux. Okay, so you are recommended to look at this derivation to confirm the amount of force is equal to this parameter. It's proportional to the number of terms to the amount of electrical current, and is also proportional to the gap distance and the area sizes. All right, so this forces produced by magnetic field can be used to what? To do this, yeah, to pull things up. Okay, so many interesting application can be